solid is dissolved in R mole of liquid solvent at a constant temperature. So we want to find out that temperature remains constant, then how much heat is evolved. It means we are not increasing the temperature of the solution, otherwise that enthalpy is gone into the internal energy. So we want to find out that if you keep the temperature constant by mixing two components, what will be the change in enthalpy? And that is always defined by two values, T and R, at a given temperature, and how many R moles of liquid solvent you are using. That depends on this. It means how much dilute solution you have. So like you have one pure water, and for example, 100 mole of water. We talk about mole because R is mole here. So you have 100 mole of water and you put 1 mole of NaCl inside and you mix it. Whatever the enthalpy change occur at a constant temperature is called enthalpy heat of solution, standard specific heat of solution at a given temperature. So this data again for various components are available. Again, those tables are available. And similarly, when you have one particular solution, you made it like this one with R number of moles of one solvent, and you have similarly another solution, for example, concentrated solution, and one is dilute solution. Now, if you mix this two solution, what will happen? So you are after all mixing two solution, making third solution, which will have different concentration, in which again you can define what is the value of R, means for 1 mole of solute, per mole of solute, how many moles of solvents are there. So that mixing, when you mix two solutions, it is called heat of mixing. That also we can indirectly calculate based on this data. So there is one table, interesting table given here. I put it in PPT. So this is the table given in your textbook. Heat of solution data at 25 degrees Celsius, 1 atmosphere for HCl and water. So like this, you will find this kind of data, or some estimation techniques are available where you can estimate heat of solution for different solvent and solute. So here, for example, if you have a HCl only gas, its heat of formation is minus 92,311. It's only HCl, there's nothing else. Now, if you add 1 mole of water into it, so you have 1 mole of HCl and 1 mole of water, you mix them together. Then the heat of solution, total heat of solution is this much. That is given by this one. And this is the integral heat of solution. So that the first part heat of solution is this 75,000, and then this x-axis, now they have shown you that if you put n number of moles inside, this heat of solution will keep on increasing, and one point it will stabilize. Because now here what is happening, I'll show you the two extreme cases. Case one here, you have 1 mole HCl and 1 mole water. So you have 1 mole of each, and you put them together. So they will arrange themselves in somehow. Now, when you have same thing here at the end, you have 1 mole HCl and 50,000 moles of H2O. So you can see that there are lots of water, and there is only some 1 mole of HCl has to adjust somewhere. That will have a different heat of solution. So if you keep on adding water, the heat of solution, integral heat of formation, or you can say integral heat of solution, which is cumulative here, this is the incremental. Means if you add 1 mole, this much change will occur. Minus 26,000 joule per gram mole of HCl, that much change will occur when you add 1 mole of water in 1 mole of HCl. Now we had 1 more mole, so now we had 2:1 ratio here. In that case, now increment will occur between these two cases is minus 22,593. But if you want to find out integral from the beginning, means from pure HCl to this solution, then that incremental change is this much, minus 48. There is summation of this. Similarly, if you add 1 more mole of water, then you will have a change of 8,000, minus 8,000. So now you can see that if you keep on adding solvent, the change in enthalpy is reducing. The increment which is happening here, that amount will keep on reducing. And at one point, the solution is so dilute that increment will be negligible. Here you can see the difference, minus 26,000 enthalpy change occur. And now at the end, when the solution is very dilute, 1 mole of HCl and 50,000 mole of water, the change in enthalpy is minus 146 joule only. So at one point, this last point they are showing here, dotted line, is the enthalpy, integral enthalpy of solution for a very dilute solution. So this remains approximately one value, they have fixed it, and they have defined that last value as infinite dilute solution. I think you have heard this in thermodynamics somewhere. So you have infinite dilute solution. So for those cases, because we have a lot of solution in industry where we can easily, I mean, approximately we can assume that it is dilute, very dilute. So in those cases, this value is available, this last value. So again, you have a table of various solvents dissolved in, say, water and other solvents at 25 degrees Celsius, and at infinite dilution, these values are available. So this is one useful data. So how to use this table? So I'll show you here. So for example, you have 1 mole of HCl and 15 mole of water. You have this mixture. So I mean, this you have a mixture of HCl and 1 HCl and 15 mole. This is the mixture you have, and this mixture you have 1 mole. Just for convenience, we take 1 mole of this, and you have another 1 mole of HCl along with 5 mole of water. So you have one solution this, another solution this. For example, you prepared in the lab, and from both of this beaker, you took 1 mole of each and you mix them, and you get 2 mole of H2O, and now this will be 10. You can make some simply algebraic calculation here. This 5 plus 15, 20. So now you have total 2 mole. So here 1 mole HCl and 10 mole of water. So now you want to find out that when you mix this two type of solutions, what will happen? What enthalpy change will occur here? If it is ideal, nothing. We can easily calculate from specific enthalpy of each solution separately. But in this particular case, you have the data available. We can find out how much enthalpy change will occur due to mixing, just due to mixing at a constant temperature. So we have total enthalpy changes, the enthalpy of final solution minus enthalpy of initial. So in this case, enthalpy of the final solution is this 2 into, so this is HCl 10H2O. So where is HCl 10H2O is here, enthalpy. So this is nothing but enthalpy of formation after all. It is the integral one. So this is the cumulative enthalpy. So you have minus 69,000 here, minus 1. So this minus inside big bracket here. So remaining is the total enthalpy of the feed solution, that is this 2. So here 1 mole of this, and 1 HCl 15 H2O. So that is 15 H2O is 70,989. And another one is 1 HCl 5 H2O. So that is 1 HCl 5 H2O is this one. So when you want to find out what is the enthalpy change occur when you mix two different solution, you can just simply use the integral heat of solution, cumulative heat of solution available in the table for that solute and that solvent, and you can use this, calculate that one data. Right, this is a small part which normally we neglect. Now if you convert this in kilojoule, how much it is? 3.9 kilojoule. And normally in our cases, all other enthalpy change Q values are in thousands. In that case, you change 3 kilojoule or 4 kilojoule, will have very less effect on the other calculation. So unless this is this case where you heat of solution is significant, like if you go and check, you know that when you mix H2SO4 and water, what happens? There is significant amount of heat generated. So at that time we cannot ignore it. Here you are getting already 3.9 is okay. I mean, you have to compare that what is the actual process, in which context we are talking. If other quantities are around this value, we keep this heat of solution in the calculation. Otherwise, we can neglect it for the initial calculation for the energy balance. Right. So this is the one small part. Just in case you have one separate question is asked on how to find out heat of solution of this kind of data are given of a new solution from given initial solutions by mixing, you can calculate it. But this, for the moment, in energy balance entire problem, we are not going to use with any other problem. It may be asked separately only to calculate heat of solution. Okay, so this we talk about that 5 parts we are talking. I'll come back to the beginning. The 5 points are this one. So pressure change, temperature change, phase change, mixing, that briefly we discuss, and entire chapter 9 of the reference book talks about chemical reaction. So there are several examples are given in the reference book. You can go through it. Starts, we have already done one, and second we did today. This is the one from textbook, and this one we did today in the morning. And the second example, C3H8 oxygen nitrogen, and you get the product. And you can do it by two different methods. One is this, and second is the taking the element as a reference, and you can take it as a C and H2O2 N2 as a reference state, and you can carry out the calculation. Right. So these two methods are there. So any one method convenient for you, you can use it. And as long as delta HR is given, you can use directly the first method. Delta HR not given, you can use this method. So this is done. Okay, here is another example. So you have ammonia and oxygen. So it is again combustion. Reacts gives you NO and H2O. Now they have given already the reaction and enthalpy of reaction. And here this is given already that this is H2O vapor. Based on that, they have calculated this delta HR. So the question is 100 mole of ammonia, mole per second of ammonia, and 200 mole of oxygen at 25 degrees Celsius. So this is good. Once you see 25 is your one part, this or all are zero enthalpy, are fed to a reactor in which ammonia is completely consumed. So your conversion is 100%. The product gas emerges at 300 degrees Celsius. Calculate the rate at which heat must be transferred to or from the reactor, assuming operation at approximately 1 atmosphere. So one thing you understand that this question you have to answer correctly, that whether you have to supply the heat or you have to remove the heat. That only you can come to know once you do the entire calculation of delta H for this case. So here you have initial enthalpy, you can take a reference state 25 degrees Celsius. Enthalpy of reaction is given. So you can take each molecule separately and define reference state. So one convenient way you can do here is simply take the NH3, ammonia, O2, what else you have? NO, H2O, and that's it, O2. You can take them as a reference state at 25 degrees Celsius. So your enthalpy table, first enthalpy table, inlet enthalpy table, all these things enthalpies are zero. You can simplify it. You can put this to R zero. And then remaining only 3 enthalpy left to calculate is this, this, and this, and this is already given. So in this case, see 100 mole of ammonia reacts and 200 mole of O2 reacts out. So material balance is done already. So here you can see that 1 mole of NH3 react, 4 mole of NH3 react, you get 4 mole of NO. So 100 mole NH3 reacts, you get 100 mole of NO. So this is correct calculation that you are getting completely, NH3 is completely consumed, 100% conversion. And water is produced 4:6, so 100:150. And O2 is consumed 4:5. So for 100 mole of ammonia, the O2 consumed will be 5 by 4 times of ammonia. So remaining O2 calculated here is 75. So 125 mole is consumed. So that material balance part initially. Now next thing left is 3 enthalpies calculation. Enthalpy of NO, H2O, NO2 in the outlet part. These two are zero. So here I'll give the name, say for example H1, H2, H3. So this H1 is nothing but enthalpy change of nitrogen oxide, NO, from reference state to the final state. And final state here product gases are at 300 degrees Celsius. So now you have two options. You can use CPDT formula, or we can go back and verify if in the physical property table you have that properties are given of NO. So here you don't have. So in this table you don't have NO, so you have to go and read the CP value of formula of NO. Okay, so here nitrogen NO here. Nitric oxide is this formula 1, and these are the ABCD values. Right, so first calculation you have to use CPDT. There is no data available. H2O is available. Right, so H2O here is in vapor form, so we have taken reference of H2O at 25 degrees Celsius vapor. So in this case you have a table with B8, H2 is here. So 25 degrees Celsius 0, and then 300 degrees Celsius is 9.57. So that you have, and oxygen also we have. So it's a straightforward calculation here. So delta H total delta H of this process is equal to molar flow rate multiplied by its specific enthalpy of product minus inlet, by chance everything is 0, and plus enthalpy of reaction. This is per mole reaction, so you have to multiply it by extent of reaction. So here extent of reaction is easy to calculate because ammonia is completely consumed. So we can take this as a for the calculation of psi. So here 100 moles are reacting, so psi value is 100. So you can use that for the calculation. So once you get this, 100 moles are reacting and the stoichiometric coefficient is 4. So minus 100 divided by minus 4. So you get 25 mole value of psi. So 25 multiplied by this will give the delta HR. Right. So see, the problem of reactions are, one part is this way where you have enthalpy of reaction. You can do it this way. And if you don't want to go by this method or the data are not available, you can take it N2, O2, H2 as a reference state, elements as a reference state. And in that case, you need enthalpy of formation of each component plus enthalpy change due to temperature. That two parts you have to add. Okay, when the process is a batch process, you can also you have a simple equation like this one. It's easy to do it manually even. So only when there is a T cube and T raised to 4, it's too long. So sometimes the simple formulas are given and they ask you, for example, calculate the heat required to raise the 200 kg of NO from 20 degree to 150 degree at constant volume. So you can calculate delta U is equal to CV dt. And then we have the another formula to replace, CV formula to replace here, and you will get the answer. Okay, now I want to just highlight one thing because this thing will come again in the next semester, heat exchanger. Okay, now when you see this reaction part is over. So when you see an example of heat exchanger, you have to understand that there are two fluids. One fluid will enter, you will see the arrow here, is entering here, and you will see it's leaving from the other side. So here you have water, liquid, 25 degree, 5 bar. And it is again same mole or molar flow rate. It's leaving in the state vapor, 5 bar, saturated. You will have another fluid which is entering here, 1 mole of gas, 500 degrees Celsius with composition is given, which is again leaving from the other side with same composition and same flow rate or 4 moles at different temperature. So here T is missing actually. So this is a problem of iterative calculation. But before that, I want to highlight that when you see a problem of heat exchanger and there are two fluids which are entering, it means these two fluids are not mixed. Purpose of heat exchanger is just to have a exchange of heat between them, not the mass. So it can, normally it's a continuous process. So you have the 200 mole per second of H2 is entering and leaving from here. And you have 1 mole per second of gas, for example, entering and then leaving from here. So what arrangement they have inside is, you know, the heat exchanger is like you have tubes. So inside the tubes, you have, for example, water is passing inside. And outside the tubes, they have hot gases. So tube will be like a barrier to avoid the mixing between them. Means the material will not be mixed, but the heat will be transferred from the gas, which is at 500 degrees Celsius, to this water liquid, which is at 25 degrees Celsius. And it will be by the time it reaches the end, it will be converted into saturated vapor at same pressure, 5 bar. So in this case, only heat transfer is occurring. No mass exchange take place between two streams. So that's why you can see this and this are given. So in case in the exam, if I give you only this data, you have to understand that whatever this stream, whatever this fluid is entering, will leave it as it is. There will be no change in mass. There is no mass balance in heat exchanger. Similarly, there is another stream which is entering with a particular flow rate, will leave as it is with same concentration. There will be no change in the concentration and the flow rate. Only thing will change is this temperature. 500 degrees Celsius will become something. That is the question they have asked. So in this case, we can use the overall that calculation that Q is equal to Q plus W is equal to delta H plus delta IK plus delta IP. We put other things 0, so you get Q equal to delta H. And now in this case, heat exchangers are normally insulated. Means we are not sending the heat outside the system. We are only having heat transfer between these two streams. Means this stream will lose the heat, this stream will gain the heat. So it means the enthalpy change in this particular stream, this delta H, that is equal to enthalpy change in this stream. So it means this gas will lose the heat and it will give away the heat to this one. So it means if you know the delta H of this particular stream, you can find out the delta H of this one. So in this example, they have not given the temperature, so you will not be able to calculate enthalpy of this stream. So you can write all the equations and where the temperature will remain a variable. And you have the other side, you have all the data are available. It means this is your 0.2 mole of water at 25 degree Celsius and liquid. And you get the saturated steam at 5 bar, 0.2 mole. So you can find out enthalpy from saturated steam table. This you can find out from the CP, or you can find out from the saturated steam table at 25 degrees Celsius, liquid water, what is the enthalpy? And you can take the difference of this two, you get the enthalpy change, multiply by the 0.2 mole. So enthalpy change on the one side of the stream is available. So that enthalpy change, delta H, is equal to enthalpy change in the stream. That we can write as a formula. And in this particular formula, when you write this delta H enthalpy change, that is the enthalpy of this minus enthalpy of this. So enthalpy of this we can calculate. We have information available, CO and a CO2, how much and what temperature. But this is not available. So this formula here will remain in terms of temperature. You will have temperature is variable. So you'll have CPDT formula where T1T is missing. And then based on that, now the process will be iterative, that you will try to set the temperature in such a way that the delta H of this delta H of this stream will be equal to the delta H you calculated from this two streams. And that's the energy balance of a heat exchanger, simple. This looks complicated right now because we are introducing CPDT and all other calculation. But in next semester, when we actually do the heat exchanger energy balance, we'll simplify it. We will not use that CP formula, we'll take it average value and some other assumptions. Based on that, we'll do the calculation. So let's take that simple. For example, we have to choose a reference state whenever energy balance is there. So first is CO and a CO2, two components are there. So we'll choose this as a reference state, so it's easier for enthalpy calculation. So 500 degrees Celsius and CO and 500 degrees Celsius CO2, both are as a reference state. And H2O, we take it as a triple point because it is the steam table is prepared based on this data. And then we do prepare a table. So in this table, see, there is no meaning of this actually. This is same. So here 0.08 mole. So we are assuming 1 mole is there, 8%. So 0.08 mole, 0.92 mole. It comes, it enters and it leaves. There is no material balance here. And similarly here, this one, in this example, this 0.2 mole, they converted into kg. Because the steam table, if you refer, the data are given in kilojoule per kg. Whereas the table B8, the CO and a CO2 data are available for H cap in kilojoule per mole. So this combinations, when you see, you make sure you write the units for each enthalpy. Now only thing left is this is 0 because we set the condition in such a way. So only part left is this H1, H2. Exit temperature, we don't know right now. So H1, H2 are missing. And H3 cap, which is the inlet enthalpy, and H4 cap, water saturated steam outlet enthalpy. That 4 things we need, in which these two parameters, H1 cap, will be calculated from reference point. So the temperature is missing. So we know that in heat exchanger, this is a hot stream, 500 degrees Celsius, and this is cold stream. So this temperature will go down, and this temperature is going up. It is